Okay, great. My name is Liam Rose. I'm with the Health Economics Resource Center at VA Palo Alto, and I'm here with Laura Graham, who's one of my colleagues here at HERC. She'll be handling questions, so feel free to answer the questions in the Q&A panel throughout, and I'll stop and address those as they come in. So today's talk is on RDD or RD, and it's just going to be an introduction, some practical advice to get you going. Is this something you want to use or something you want to read if you're someone that reads papers on this? So RDs are a quasi-mental experimental design, and with the right setup, the estimates are causal. This is something that's really important. They have kind of a lot of requirements that I'll talk about. But the reason that we go through those requirements is to get estimates that might be causal rather than correlational. So we're going to go through some fundamentals, how to interpret them, so if you're reading a paper, and how to implement them. And we'll do very briefly how to implement, but I'll give some more resources on how to do that down the road. So we'll start with only poll question for today. I'm just interested in what your interest is in RDD. Are you interested in reading and interpreting papers or using it on projects? Expanding your analytic toolkit, or just curious about it at this point?
The poll is open and the responses are coming in. Let's just give it a few more moments, and then I'll go ahead and close the poll once it slows down. Let's see, and okay, I'm going to go ahead and close that poll. And the responses that we got, 12% said A, 16% said B, 45% said C, and 22% said just curious. Back to you.
Awesome. Yeah, so a lot of people are interested in using it, which is great because I have some code examples in here that I worked on. Okay, so some basics. When you can't do a randomized controlled trial, you know, whether it's just too expensive or unethical or whatever it is, you often have many confounders, and some you can see and some you can't. This gives us a admitted variable bias, and you could have just on the observables, you can use matching, you could use propensity scores, you can use machine learning, but there's some confounders you just can't look at. So, you know, you can't include things you don't observe in a model, no matter how hard you try. So instead, what we do is we use some threshold or cutoff to determine treatment status. So the treatment is you're exposed to this policy, no treatment is no exposure to the policy. And under the right circumstances, individuals will be similar, close to a threshold. And I'll go through some examples on how that might work. So these individuals close to this threshold, where some of them get the policy and some don't, some of them, they'll be very similar, but some of them will get it and some will not. And this can give us the causal effect of this policy or this rule or whatever kind of thing that we're trying to evaluate. If you like DAGs or conceptual models, here's one. They don't do a lot for me, if I'm being honest, but I know a lot of people like them. So in this example, we have X, which is the thing we care about. It's related to both the treatment D and the outcome. With an RD, as X gets arbitrarily close to some cutoff, C naught, then it's only going to affect Y through the treatment. And this is what we want in a very nice, this graph on the right here. That's what you want, right? You don't want your thing of interest to be affecting both the treatment status and the outcome. You want it to just go through the treatment status. Personally, I find it much easier to understand through examples. So here's a nice example that's been used in the literature in the past. So the policy is legal access to alcohol, specifically in the United States. So when you're 21, you can buy alcohol. When you are 20, you cannot. And this makes it much easier to access alcohol. And the thing is, 21 is kind of arbitrary. Our birthdays are arbitrary, right? You wake up one morning and you're a whole year older, but you know, you don't typically feel any different. But by comparing the mortality rate of individuals just below 21 to those just over 21 with the RD approach, we can estimate the causal effect of having this access to alcohol that suddenly becomes legal when you wake up one morning. on what does that do to our mortality, and it's best shown with figures. And I'm going to say that a bunch of times in this talk probably, but figures are really the big thing in RD design. Okay, so what is going on in this figure? We see something really big happening in the middle, and we find that, so on the x-axis, excuse me, I should back up. So on the x-axis, we have age centered at 21, and that's in years. So 0 equals exactly 21, and then a 1 on this graph equals 22, 2 equals 23, etc. And then on the left-hand axis, the outcome here is motor vehicle accident deaths per 100,000 people. And what you can see here is that right when people turn 21, there's a pretty substantial jump in the mortality rate due to motor vehicle accidents. Now you notice I haven't said anything about alcohol in this graph, right? It's just all I'm doing is showing like, look, here's people's age and here's people's likelihood of dying in a motor vehicle accident. But this is what the RD design gets us, right? We're just looking at this policy that happens when you turn 21. And this policy happens to be legal access to alcohol. Okay, so there are some requirements, but it does have a lot of applications. It requires a lot of data. And I think there's kind of this interesting anecdote where this method was invented in the 60s, but it really didn't take off until the late 90s with a couple economics papers. I think they were all in 1999, actually. And one theory is why this didn't happen is that there wasn't the capacity of data that we have now in the 70s and 80s and 90s to be able to run this, because you do need a lot of data and you need a specific cutoff. However, we love cutoffs as people. We like to say things, you can even see it happening now with COVID, right? It's like, okay, anyone over 75 can get vaccinated. Okay, now over 65. We tend to think of them as kind of fair. Even if there's some arbitrary cutoff, we say like, okay, people on this side can, people on this side can't. So a lot of scenarios we can look at. School entry age. People are, you can see like young for your age or old for your age when you enter school. People have done that one a lot. Elections, super popular in political science. And if we have time, we'll go through an example on that. Test scores. Test scores were actually the original example of this. If you've ever taken a test, sometimes the difference between an 89 and a 90 on a test is just kind of luck of the draw. And that's how it's applied. Sometimes in that specific example, if you got 1 point better, you got a scholarship. If not, you didn't. Birth weights, Medicare eligibility age. We'll go through that one, a couple examples of that one here. And it's attractive because of simplicity. It's just OLS. It could be a local linear regression as well, but it's usually just OLS, and you can draw a nice picture. And we love pictures. You can share them on Twitter, and show how great your study is or whatever. And one note here is it's not an event study and it's not an interrupted time series. These are different. An interrupted time series is a different study design, and those just always have time on the x-axis. RDD won't have time on the x-axis. The event study can work in certain contexts, but you have to make some additional assumptions about things that are happening at the same time that you don't have to do with RD.
Hey, Liam, we have a question.
Yeah. Great.
This one comes from Maria, and it's when looking at the comparison groups, how far from the cutoff are these groups comparable? For example, for the age of 21 cutoff, would we only look at those who are 20 and 22, or could you look a bit further back?
Yeah, so I'll go through that in a minute. That's called the bandwidth. And it's actually, let me hold off on that because I want to go through it while we're looking at a figure. And we'll come back to see. That's a really good question. But I will come back to it. So here are some requirements for it, just to have this design. What you need is a continuous measure. Age, very easy one. Age is continuous. You can't skip ages as much as we'd like to. You can't have something that's blocky. If there's big jumps in your x-axis, then it won't work very well. So if you need a cutoff, you need some rule. It cannot be manipulable. Again, age is a very good one. You cannot change your age. You typically can't change your test score, but sometimes this doesn't work. Sometimes people are able to get on one side or another. This is something that actually goes wrong a lot of time with interrupted time series, where people wait to do something because they know that something is going to happen, and that means it's manipulable because they waited for the policy to start. It has to be arbitrary. You can't have a policy that says, I'm going to give it to a certain group of people. It has to be somewhat arbitrary. 21 is a very good example. 21 is a super arbitrary age. Cutoffs for you can think of there's some examples of cutoffs for drugs and cutoffs for testing, medical tests. Usually some arbitrary cutoff. And then you need data, lots of it. Okay, so let's do some examples, and we'll get back to that question about how far apart, specifically with the bandwidth. So here we're looking at some examples, being able to read and interpret RD estimates, starting with that age 21 example. Again, if you're not American, age 21 is when you're legally allowed to purchase alcohol. Okay, so here is a couple combined figures. And the bandwidth, which is what we call how far away from the cutoff, here is 2 years. It's typically expressed as one-sided. So here it's 2 years. And here there's accidental injuries on the left axis, and then there's alcohol intoxication and deliberate injuries on the right axis. And you can see this is basically the same as what I showed before. There's some big jumps. This is emergency department visits, not mortality this time, just in case that wasn't clear. But there's injuries by other people, and there's a big jump in alcohol intoxication. And here are the numbers. So here's what it looks like. I'm going to jump back and forth between these two slides. So if you have yours open separately from me, that's what I'm doing. So the estimates are on over 21. And over 21 gives us the size of that jump. If I go back to this slide, and I could kind of eyeball it, but this gives me the exact amount going from left to right. And in this case, there is a 71 per 10,000 people overall. And if we're looking at alcohol, that black line, the big one that you can see very clearly, it's 17.2, an increase in 17.2 ED visits per 10,000 people for alcohol intoxication. And if you go back to the figure and look at the right axis, that looks about right. And then we get standard errors on that too, which is nice for throwing up our stars and saying it's statistically significant. Okay, and then the constants, if you do this right, if you set it up the right way, the constants give the just before estimate. I put that in quotes. It's like the left side of the jump. And this is really useful for interpretation. And I'm again looking at column 4 under alcohol. And the constant is for those almost age 21, there's an ED visit rate of 54 per 10,000 for alcohol intoxication. And what that means is there's a 32% increase in ED visits for alcohol intoxication. And the way I got that right is I divided 17 by 54. So again, looking at column 4. So that's why it makes it nice for the interpretation. So the 17.2 gives me how much it increased, and then I can use the constant to get the percent increase, which is obviously quite useful for writing up your papers or looking at the policy. Here's another example. I wanted to include a health example. This is HIV care from Bohr et al. 2012. Same idea. Here they're using a slightly different regression technique, but you get it, the same idea, 18 percentage points. And they're using HIV tests where there's a cutoff for people who continue with their HIV care, and that's the outcome. And they can see people who have their CD4 count, when it's higher, they're much less likely to be continuing their clinical care for HIV. And the same idea as I just went through. Column 2 gives the estimate of the jump, 17.9% more. and then retaining at 12 months, and then that equates to a 56% change at that cutoff. Okay, implementation. Here's where we'll get to the idea of bandwidth as well. So this is what I said before. You need a continuous measure. This is I usually just call it the running variable. Sometimes people call it the forcing variable. I like running variable the best because it's like across the bottom. It needs an arbitrary, non-manipulable cutoff, and it needs a smooth distribution of characteristics besides the treatment at this threshold. This gets into this idea of comparing people who are, 21 and 22 or 19 and 23. It has to be smooth. And so what do? We need to plot it, and you need to plot a lot of things. I make hundreds of these when I'm doing this work. So you need to make a few decisions. The best practice, like I said, is to plot everything. You don't want your results to depend on any particular choice you make in the plot. You want to be able to show that, there's a real effect here, and it's not just because I cherry picked the best looking figure. So you start by plotting the running variable against the outcome. This looks terrible, but it illustrates the point. This is days to 21 now, and you can see this is the violent climb rate relative to age 21. Really crude figure, but it's really messy. Down at the left-hand side of the figure, you can see something messy that we don't want to deal with. That would be the age 18. And that gets into stuff like juvenile court and such, so we don't really want to look at that. We want to zoom in a little more towards the center of this figure and try and clean that up a bit. And the way we do that is we bin the data to make the figures a bit more clean. And what you do is you just average, create clumps of data, and put them as single dots instead of the mess of dots that we just saw. And it's important to make sure this bin doesn't stand the threshold, otherwise this hurts your interpretation. What I mean by that is you don't want to group to be people that are on one side not getting the treatment with people on the other side who are getting the treatment. So make sure that they meet in the middle. And then you don't want to run the regressions on the bin data for the most part. So you use the predicted values of the full regression, and then you put it onto superimpose it onto the figure. And that's what that looks like. So here, what we've done is we've taken a bin size of 20 days. So this is the same figures before, but I've just cleaned it up. I took away those age 18 folks, and then I put the 20-day bin. So what that means is for every 20 days, I took an average of the outcome and included that in the figure. And you can see, I haven't even run a regression here, and you can see that there's a very large effect, and that's kind of what you're going for. So density, this is a big one. You have to make sure the density is smooth. This is called a McCrary test after the guy who invented it, Justin McCrary. You want to make sure that the distribution of the running variable is smooth around the threshold. And this actually ruins a lot of RD designs. It can be quite annoying. Rounding and measurement error can render otherwise valid applications invalid. Here is I think a very good example. On the left here, this is a pretty famous paper where they were trying to look at newborns who had low birth weight, because low birth weight babies got extra attention. And so they were trying to figure out what's the effect of that extra attention. The problem is, as you can see, is there are these huge lumps in the density. And what that corresponds to is that grams, because it was 1,500 grams, was considered low birth weight. But a lot of times the babies were measured in pounds, and it created these big lumps. And you can see there's this big lump around 1,500 grams. And so when there's you can think of this as like a randomized control trial. You wouldn't want to have 1,000 people in the treatment group and 100 people in the control group. That makes it very hard to compare. And so you're not sure, especially in an RD example, if the treatment effect is due to a whole mass of people on one side or it's because of the treatment itself. So this one on the right is a little better, I think. This is age relative to pension age. This is from England. It's just the number of people and how old they are. And you can see this is not perfect, but it's okay. It's relatively smooth. It doesn't have to be like a flat line is what the point I'm trying to make. Here you can see kind of some of the seasonality in births, but around age 0, which is the pension age 60 or 65 in this specific example, it's relatively smooth. And that's what you're looking for. So you just need to show that. Bandwidth, okay. So this is the question that was brought up earlier about how far away are these estimates valid? So bandwidth is essentially just the range of X. You know, in a lot of figures, when you're plotting, you don't give a lot of thought to the range. You just do what looks good. But this is actually very important in this context because this determines what is in the regression. So there's been a lot of work done on this, and it's called these optimal bandwidth procedures. And you can run this CAN procedure and it'll tell you, hey, for this outcome, this is how much we think should be included in the regression. So in the 19 to 23 example, it probably won't spit out 19 to 23, but it might spit out a certain number. And it has to do with how many observations you have and what's your outcome and how much variation is in your outcome. But I think beyond just the bandwidth procedure itself, it's also good to just try out a range. And ideally what you want is a figure that shows robustness. So you plot the RD estimate as a function of the bandwidth choice. And this is how it looks. And so in this figure, this is again from the pension example, what you do is you just take the range of X and expand it by 1 and redo the regression, expand it by 1, redo the regression, and over and over and over. And you show the point estimate on the jump for each individual regression at each individual bandwidth. And you plot the bandwidth is on the x-axis. So you say, here's the point estimate at 50 months. Here's the point estimate at 75 months. And you just want to show that, you know what, it's like any regression, you're not going to get this perfect magnitude no matter what choice you make, because there's always some sensitivity, but it's relatively in the same range. It's not like some are negative, some are insignificant. They're all in the same relative range. And here's the idea about whether groups are comparable.
Hey, Liam.
Yeah.
Do you have quite a second for some questions?
Yeah, of course.
Awesome. So we have 2 good questions that have come through. The first is regarding the bin. So in comparing bin values, pre and post arbitrary cutoff, are the statistical methods the same as for linear regression?
Yeah, so the bin is only for plotting, but plotting is so important in this context that I thought I would include it. Technically, if you're not showing a figure, you don't have to bin them at all. Because like I said, well, I haven't run a regression in this figure that I'm showing on the screen right now. There's no regression methodology happening. What I would do, and if I had this example, is I would run the regression on all the data, and then I would get the predicted values of that, and then superimpose that line onto the bin data. But fundamentally, the regression is just all the data. There's no binning involved.
Awesome.
Yeah.
And one more quick question. This one's from Nick. He says he's might misunderstand the bin sizes. And so how does, if you have bins equal 20, not overlap with the birthday when you have a time period of 365 days? Because 365 divided by 20 ends up as being like 18.25. So is that just a rough estimate of dealing with a year of making sure that your bins are appropriately sized on either side of the birthday? Or is there a bin period where it includes a birthday and maybe you exclude that interval?
So I care most about the middle, because I don't want it to go over 21 in this example, because what that would do is would average across the boundary, and I don't want to do that. What I do instead is there's some fudging on the edges. So yeah, you're right. It doesn't perfectly overlap the 19th birthday or the 20th birthday, but I don't particularly care about that. I'm just trying to show that there's a jump at the threshold, but at the point where there's no threshold, then it's fine to average across.
Awesome. And then one more quick question that just came in. Is it feasible to combine this RD with differences in differences, like a pre-post regression discontinuity design?
Yep, absolutely. A lot of people have started doing that. When you need to, I mean, it has a lot of like data requirements, right? You need a policy that happens over time with an RD design. So, but yes, people have done that. You know, a specific example, like how many people are getting insurance at age 65 with pre and post ACA.
Awesome. You're all set. Thanks, Liam.
Yeah, and if I don't clarify the question, whoever wrote it in, please follow up. I'm happy to talk more about it. But here is, I'm going back to this question about comparability, which I think is a good one. So in an RCT, you run a balance check, right? You're like people who got pill versus people who got placebo, and then you run like a t-test or an f-test to see if those two groups are the same on whatever stuff you have about them, your age, their gender, their race, their SES, their comorbidities, whatever information you might have. You do the same thing in an RD, except instead what you want this time is that it is smooth at the threshold. Now, what this means is that you don't care, like for our 21 example, you don't care if 19-year-olds are on average different from 23-year-olds. What you care is that things are not changing discontinuously right at 21, because that could indicate, you know, essentially you're just having a different group of people on one side than the other. Because essentially what this method is doing is saying, you know, it's not saying that you want to compare 19 to 23-year-olds, because you're not comparing means. What you're comparing is the evolution of this age trend on one side versus the evolution of the age trend on the other, and showing that there's a big jump in between them. So it doesn't have to be perfectly balanced between 19 and 23-year-olds. What it does have to show is that there's no change at the threshold. So here's an example. This is the change in potential confounders at age 21. So here's the proportion married, the proportion employed, the proportion without a high school diploma, the proportion that have some college, the proportion that have health insurance. And you can see these are standard errors below. None of these are statistically significant, so that's what you want. If an alternative is if you saw that, you know, there's a huge portion of, you saw a significant result on perhaps the proportion that are married or proportion employed, you're not sure if other things might be wrong as well. Essentially, it's like an RCT where you're showing that the observables are balanced with to give credence to the idea that the unobservables are balanced as well. So if I had another column for how much do you like alcohol, how often do you go to bars, or what is your inherent, your genetic predisposition to alcohol intoxication, things that it would be super hard to measure and not in surveys, those are likely balanced as well if these are balanced here. So to kind of sum that up, you're not trying to compare people at the edges. However, you do want to have some range truncation to be able to focus on the relevant policy. I mean, certainly if you're looking at Medicare, like we will in a moment, you don't want to be looking at 30-year-olds and 100-year-olds. That just introduces a lot of noise. And there is like a bias and precision trade-off here at some level, and that's what a lot of the bandwidth selection procedures are taking into account. But like I said, there's an art, I guess you would say, about thinking about, hey, are there other changes? And in our 19 to 21 example, 21 example, a lot of this was done before tobacco was raised to 21 in some states. So that would make it harder now. But 18 is a big one, right? You wouldn't want to include the 18-year-olds because there's a lot of things that happen at 18. Not a lot happens at 19, fortunately, so it makes it a lot easier. Please let me know if that didn't answer the question. This is just a small thing, polynomial order. Good idea to try. You could use different polynomial orders in the regression or a local linear. That's also very popular. Good idea to try out some different ones. Too high is almost always a bad idea. You don't want to have like a fifth order. And the reason for that is you can be very sensitive to outliers. If you think back to our 21 example, maybe I can go back to the figure real quick. There's a huge birthday effect, right? Sometimes your 21st birthday goes wrong, and you don't want to have a situation with your RD is entirely driven off the 21 effect. What you see here, right, is it's not a spike at 21 and then it goes back to where it was right before 21. It's a jump that continues. And so, you know, a very high order polynomial in the regression would just pick up that and overestimate the effect of alcohol and violent crime arrests. So really what you want to do, you could even do something called a donut RD where you take out that 21 just to show that it's robust. But in any case, you don't want to have too high an order in general. Okay, some code snippets. How are we on time? Oh, we're doing great on time. We can go through the code. And if there's questions, if I'm going too fast, we can double back to things. Please let me know. So I have a very quick example in orange data, and I think there's other packages as well. I'm not really aware of them, but there on the bottom here, there's some CAN packages you could use. Those are nice if you just want to get started very quickly. This is a more manual example. Going through R, you have some data. You create the running variable. This is the 21 example, where the running variable is age minus 21, so you center it at 0. And then you make some interactions. So this will give me a third order polynomial. And then you create this variable z, which is just, this is the treatment variable. If you're over 21, you get the treatment. If you're under, you don't. And it works the same in Arn's data. Okay, so now we have an example, time permitting. So we do have time, which is great. Okay, so this question from Bila in 2015. Does the party of the state governor matter for the black-white earnings gap? If you're not from the U.S., that might not make much sense, but the political party of the governor of the specific state you're in, does it matter for the difference in earnings between black individuals and white individuals? And so they use, this is one of those close election RDs that I mentioned, very popular. There's a controversy a couple of years ago where some of them maybe didn't work, but that seems to only be the case in certain House elections. You could read that literature if you're interested, or I could point it to you. But here they use data from elections, and they use data from the current population survey, which is the Bureau of Labor Statistics survey. Okay, so I'm just going to go through this. I know this is very code heavy, but I want to just talk about how it might look. So load some libraries. I read in the data. The data, this is just replication data. You could also replicate this if you like. So I read in their data. I slim it down just so we can see what's going on. So I include these 5 variables. And this is a person level data set. And the black 2, I don't know why they call it black 2, but that determines whether the individual is black or not. Wages, that gives their wages in that period. Margin, GGG, again, I don't know why they use that notation, but that's the margin of the vote. So by how much did the governor win this election? And then total hours, that's how many hours they work. And then there's a weighting variable. I just included that because we need it for the regression, because this is a survey. If you worked with surveys, there's survey weights and all that. So I'm just trying to give an idea here of how you might think about your data setup. And in this case, it's an individual level data set because that's what I want. I'm going to do my regressions on the individual level. I'm going to have their outcomes. I'm going to have what defines their treatment, in this case, the margin of victory. And that's about all you need, really. Okay, so in this case, the first two lines here are the regression. I'm doing this on the total hours they work. And so I have this variable Z that I mentioned. That just means if they got the treatment. I have the margin of victory, and I have the interaction between those. And that just allows the regression slope to be different on the right-hand side than the left-hand side. But I don't even really need that, so I'm just going to comment that out at the moment. I'm going to kind of take a shortcut here. So what I've done here, first line under under political labor sample, I take out if I just want people who are black. Okay, so filter the people who are black, and then I just filter people who are earning any wages, so people in the labor force. And then what I do is I group by my running variable. So for each level of X, I want the mean hours worked. And it's weighted because this is a survey. If you don't have a survey, you might not need this weighted mean. It could just be a standard mean. Okay, and then I can make a plot, and it's that simple, really. So here I have this aggregated data where for each value of X, where X is the margin of gubernatorial election win, I have the hours of worked. And I put those in log terms because those are nice for interpretation. If you're comfortable with R, this is a very simple ggplot thing that you might know. If you're not, bear with me. It's just the same as any other program where on the x-axis I put the margin of victory, and on the y-axis I put the outcome, which in this case is log mean, which I created in the last step. I'm going to go back one step. You can see I created this variable mean, and now it is that is the outcome. And then I make it look nice. And in this case, I just used Stata's, or no, this is R. I use R's stat smooth feature and filtered it on the margin less than or greater than. And you can see that there's a big jump. So greater than 0 in this case, if in case you're wondering what the outcome and don't want to read the paper, greater than 0 means that a Democrat won the election. And you could see that that translates to an increase in the log of hours worked for black workers. Not shown is that it does not change the log of hours worked for white workers. So it does end up decreasing the black-white earnings gap. But for our purposes, just to review very briefly, I have an individual level data set. I aggregate it by the running variable, and then I plot it. And before you even run any regressions, you could do this a couple hundred times, right? You can think of different outcomes. You could think of different ranges of X. I just picked the full range of X here. You might want to think about like, oh, okay, maybe I just want to focus on some of the smaller ones. Maybe I want to try out one of these canned packages for optimal bandwidth and try it with that. But this is just a very basic way of doing this. Okay, so some takeaways. You want to make a lot of figures. You know, I went through some decisions you have to make, the different polynomial orders, the different bin widths, the different bandwidths, bandwidth being probably the most important. But you want to make a lot of them and make sure it's there. You know, you really want to have to convince yourself that you're not just picking up the 1 in 100 where there is a jump. You want to be able to say that, you know what, there really is a big jump in this policy that we can see. It is not just, of course, you can pick the best figure you want for publication, but you know, you want to convince yourself that it's there, even if you made some different choices. So try out all those different choices. Show the robustness. Show that it's not just the one figure that you picked out. Okay, so wow, maybe it went too fast. So we have a lot of time for questions. RD gives a great way to get causal estimates when RCT is not feasible. This is a good example, right, where you you can't legalize, you can't do an RCT on access to alcohol. Not really a good idea. You can't really, there's a lot of situations where it works, where otherwise you couldn't do an RCT. You need that continuous measure. You need the arbitrary cutoff that determines treatment. You need to show that there's balance across the threshold in demographic characteristics. You need to show that it's smooth. There's sometimes you have an idea and you're like, this is great. And then you look and you say like, well, wait a second, this survey only looks at people on one side of the discontinuity, and that doesn't get you anywhere. And then you need to show robustness to parameters. And there's questions. And then I also wanted to talk about a few resources really quick. Mastering Metrics is a very it's an undergrad level econometrics book, and it's really nice. And then there's Mostly Harmless Econometrics, which is a more advanced version. And then Causal Inference, the mixtape, I think is really good. This is Scott Cunningham's book. The online version is free. Scott Cunningham will actually also be back on HSR&D cyber seminar in June, so come and check that out. Some of his work on mental health would be really interesting. For some really more advanced stuff, we have Leon Lemieux. This is Guide to the Practice with Zhu and Bloom and Summers. But yeah, like I said, I think the first two are very accessible and very nice. Free version of the mixtape. It's awesome. Go check it out. So there are questions, hopefully, and this is my email. Happy to listen.
Hey, awesome job, Liam. Thank you so much. You've got some questions coming in, some really good ones too. So the first question that popped up, and this was a little bit earlier, and it was when you're thinking about things that are kind of binary, like married, yes, no, would the y-axis in the plot be a log probability or something along those lines?
Oh yeah, great question. Actually, you can't plot that. You do need to bend that one. Otherwise, you'll just get a bunch of zeros and ones, right? That doesn't work out so well. So yeah, you can do the regression on it. Obviously, it can be a binary outcome, no problem. Economists are usually fine with a linear probability model there, but you could think of something else. But for the plot itself, yes, you would need some kind of bin to get an average between the, if you had really, really nice small data, right, you could say like, okay, here's the average marriage rate for people who are 20 years old and 300 days, 20 years old and 301 days, et cetera, et cetera. But, a lot of times you would say like, okay, here's the average for people who are between 20 and 300 days and 320 days, something like that. I hope that answers the question. But yeah, if it's a 0-1, you can't just plot the raw values.
Awesome. And we've got a couple of questions that have come in along the same lines of thinking in terms of an interrupted time series and regression discontinuity. Just to give you an example, one of them is, I know you said this isn't supposed to be like a time series analysis, but do RD analyses only focus on the difference at the event, or do they also track the difference in slopes or different parts of the line?
Yeah, so it's called a regression kink design. It's, if you can do this with, I think the best example is a card paper on I think it was unemployment benefits, where if you have a change in income, there's a kink in the amount of benefits you get. It's not a jump, but there's a kink. And you can definitely look at that. And it's very similar, really, to an RD design in almost every way. It gives a marginal treatment effect instead of a local average treatment effect, but it works as a research design. But as far as like an event study, that's something slightly different. If you were just looking at the kink at a point in time, that is a bit different and not really subject to the same assumptions.
Awesome. Yeah, and I think this question kind of builds on that, which is the difference between interrupted time series and regression discontinuity, and when you might choose one over the other. Do you have any thoughts on how you would, when you might choose one over the other?
Yeah, I mean, so an event study, an interrupted time series, I mean, I would use that if I had to, because it's like, this policy came into place, and there's no way that I can look at, I can't find essentially what, if you're familiar with difference and differences, an interrupted time series is just going to give you essentially one half of difference and difference, which is not great. What it works for, I think, for the most part, are things that drop out of the sky, events that come from nowhere. I think it's been used successfully in like finance literature. If you make the assumption that there's no insider knowledge, and then a CEO dies or something like that, then you could like look at this change in the stock price, because it's a very, stock prices are traded continuously, and this thing came out of nowhere. If, on the other hand, there's a policy that's going into play, and it's known ahead of time, and they say like, okay, on the first of the month, this is when it's going to happen, then it doesn't work so well, because then people can manipulate when you do things based on when you think that the policy is going to happen and what's best for you. You optimize. So yeah, I would only really use an event study if I didn't have another choice. And RD is much more about finding the effect of a policy that evolves around an arbitrary cutoff that is not just a singular point in time.
Awesome. We've got two questions that came in regarding sample size. So one is just concerns, what are some of the typical concerns about sample size? And then another being, explain why you say you need lots of data compared to typical returns about sample size and getting reliable estimates.
I'm sorry, could you repeat that one more time?
Oh yeah, so explain what you meant by needing lots of data compared to typical returns about sample size, getting reliable estimates. Yeah.
Yeah, maybe I could go to a figure to talk about that. So like for this, well, this is in rates, so it's kind of hard to see. I guess I don't really have a good example. But essentially the issue with not having enough data is that it can get into the idea that the density is not good. So if you're missing a bunch of data points along the x-axis, you could have some kind of lumpy densities, which could drive the treatment effects that you're finding. For example, if for some reason you have a wonky survey, and going back to our 21 example, if there's a ton of 20-year-olds and you only have a few 19-year-olds, it makes it very unclear whether the x-axis will be continuous. And so if you don't have a continuous x-axis, then it's not clear whether the effect you find is because of the policy or because you just have different lumps of individuals at different places. The other issue with not having enough of a sample is sometimes these treatment effects are quite small, so you want to be able to precisely estimate, but that's an issue with a lot of regressions as well.
Awesome. And I have a fun question for you here, Liam. So the question is, do you have a GitHub? And I'm assuming this is to be able to help share some of the code that you've talked about.
I have a GitHub, but I only post fun things. Check out my analysis of the Great British Bake Off. But I don't have a GitHub with code from this example. This is from a class I used to teach, and it's from papers. Yeah, sorry, but I do really recommend. I'll double plug Scott Cunningham's book, which does have some more code examples than I have.
Awesome. And of course, these slides will be made available afterwards. So the bits of code that are included in there will also be available that way.
Yeah, that's right. Yeah.
Awesome. And we have another question here, which I think is actually really interesting to think about. If the covariates are not balanced, and I'm assuming that this is between the two time intervals, how do you fix this? Do you try to control for other confounders with the regression, or are you unable to control to continue doing the risk difference or regression discontinuity?
Yeah, I mean, it's a good question. Like here we have, so here I have 6 covariates. I mean, it kind of depends. If you're in an RCT, you know, and you have 20 covariates and you find one that's significant, that's probably what you'd expect, you know. And it's the same with an RD design. So, you know, you'd expect maybe 1 in 20 to be significant at the 5% level. That's just how it works. But, you know, it kind of depends. Like if I find one that's a little bit significant, you know, it's got a t-stat of maybe 2, and the rest are not significant, you know, then yeah, sure, that I probably convinced that, you know, I could control for that in the regression and probably other things that maybe just this statistical artifact. On the other hand, you know, even if I found that, you know, there was a 30% change in employment at 21 in this survey that I'm looking at, even if that's the only thing significant, I'd probably have to drop it as the data source or drop the project, because it's not gonna, there's something wrong with it where they're just looking at employed people on one side and non-employed people on the other, and there's no way for me to get around that difference in people when I'm looking at the outcomes. Because essentially what you want to do, it's just like an RCT where, you know, you're not really trying to convince yourself about the observable characteristics. You're trying to convince yourself about the unobservable characteristics. And if I found a huge change in employment right at 21, I wouldn't have any confidence that the things I couldn't see, you know, their motivation, their genetic predisposition to alcohol intoxication, wouldn't also be different. I don't know. So I think you think about it in the RCT context, and you know, it's perhaps the same there. You know, if for some reason you're giving out pills at the hospital, and for some reason the people who got the pills were 10 years older, you know, you're kind of up a creek at that point. There's not much you can do to salvage that. You can control for age, sure, but if they're 10 years older, there's a whole bunch of other stuff happening.
Awesome. And we've got, I see 2 more questions in here. So one is also, I find super interesting as well. So could you talk more about when you get valid causal inference from this model? So if you are using OLS, you still need all the other assumptions satisfied, correct?
Yeah. Yeah, I mean, it's a good question, but I think for the most part, I struggle to think of a time where you have this much data, and OLS assumptions will not be valid. So I think for when you need to get causal, you really need you need to show the balance across the threshold. So, you know, there's not, like we just talked about, it's not 10 years older on one side or whatever. You need to have a smooth density, so you have is so that there's not just a mass of people on one side or the other, and you need to have robustness, and then you could plausibly make the claim that's plausible. In addition to the idea that you have a non-manipulable cutoff. Manipulable cutoffs will really sink this idea that it's causal. But as far as like OLS is concerned, I like I said, I struggle to think of a time where the OLS assumptions won't be met.
Awesome. And we just had one pop up regarding disability compensation ratings, which I think you'll find interesting. So talk about RDD and rounding to create combined disability compensation ratings. And Yeah. So don't we have many, so we have many thresholds like 10, 10, 20, 30, 100% levels. Do we need smoothness over the entire 0% to 100% range?
No. It depends what you're looking at. There's a couple people who have done this or are working on this project with the combined ratings in the VA. But no, you do not need smoothness, especially with those, because it's a little bit tricky in that specific instance, because people can be at the 10 numbers, the 50, 60, whatever, without combining. So you need to, if you're looking at in that situation, you can stack on top of each other. So you can look at the 41 to 49, 51 to 59, and stack them all on top of each other. Or you can disaggregate and look at the people who are just in one particular range, if that's what you're interested in. But you do need smoothness across the particular range that you're interested in. So if you were to look at 40 to 49, you would need smoothness there. If you were looking at 41 to 49 and 51 to 59, you would need smoothness there. So yeah, you do need to have those McCurry tests for all of those. Apologies to those who are not in VA. This is just a specific question about disability ratings, but this is a general thing. Any of your outcomes, or sorry, any of your populations should have some kind of density test. That's the takeaway.
Awesome. And then one final question, which is, could you please provide a reference, and I'm pretty sure you've probably already got one after seeing your reference slides, that uses regression discontinuity design with a difference in difference approach. And one that highlights cautions would be great, if you can think of one.
Highlights cautions?
Cautions of using the regression discontinuity design with a difference in difference approach.
Ooh. Okay, I don't know if it highlights the cautions. I'd have to, I'm sorry, I don't remember the authors off the top of my head. If the asker could please send me an email, I'll get right back to them after this.
Awesome. Make a note of that. Yay. I think you've answered pretty much everything. We've got about 2 more minutes. I have one quick question that I think might be interesting, at least from my perspective, I'd like to know, as far as like having the concerns about balance. Has there been any, like using stratification to try and induce some sort of balance? Would that be some kind of method that you can use potentially?
Stratification meaning, I guess you could subset. Is that what you like? You would only look at a specific population. Yeah, that's definitely can be done. But you kind of like, I don't know how many people like, the cynical side of me says people just look at the specific population that works and they don't publish on the one that doesn't work. But yeah, if for example, you found that you only had smoothness and balance across a specific portion of your population, and that's a valid design. But you probably wouldn't report the rest of it.
Need to be clear about what we find there.
Yeah.
Yay. Well, that's all the questions I have. So I don't know if you have any final notes. It's now 12 o'clock on the top of the hour.
Sure. Email me if you have questions and check out the references.